Bonjour à tous et bienvenue ici à l'Observatoire de Genève, qui est le département d'astronomie de l'Université de Genève. Je vais juste vous dire quelques mots sur ce département d'abord, ensuite sur le Colloque Wright, et après je ferai quelques mots de présentation de nos trois conférenciers d'aujourd'hui. Alors, le département d'astronomie de l'Université de Genève, c'est un département qui évidemment étudie tout ce qu'il y a dans l'univers. Les planètes, les étoiles, les galaxies et même l'univers dans son ensemble. Je ne vais pas faire une description détaillée évidemment des activités de cet observatoire, mais simplement vous dire un mot. Vous avez peut-être connaissance qu'il y a à peu près une vingtaine d'années, beaucoup d'entre vous n'étaient pas encore nés, ici, dans ce département, le professeur Michel Mayor et Didier Queloz ont fait la découverte de la première planète extrasolaire dans notre propre galaxie, même dans l'univers, je dirais. C'est la première fois qu'on voyait des planètes autour d'autres étoiles que le Soleil. Jusqu'en 1995, on ne connaissait que les planètes Mercure, Vénus, la Terre, etc., jusqu'à Neptune, puisque Pluton n'est plus une planète. Et en 1995, on a découvert cette première planète qui s'appelle 51 Peg, dans la constellation de Pégase. Et c'est devenu un des domaines extraordinairement à l'avant-poste de la recherche actuellement, c'est cette recherche de planètes extrasolaires. Mais aujourd'hui, si nous sommes ici, ce n'est pas les planètes extrasolaires qui nous réunissent. C'est en fait une étoile bien connue, qui en fait nous réchauffe, nous éclaire tous les jours, depuis la nuit des temps, si j'ose dire, et qui est le Soleil. Et donc, je vais vous dire quelques mots sur le thème de cette année et sur la Fondation Wright. Donc, la Fondation Wright, c'est donc cette fondation qui organise, qui a mis sur pied ce colloque, ces conférences. Il s'agit donc d'un industriel, M. Dudley Wright, qui a fait don d'une somme d'argent assez importante pour pouvoir promouvoir la science auprès du grand public et aussi auprès des jeunes. Car une idée, c'est essayer de susciter des vocations pour la recherche scientifique, car vous le verrez, la recherche scientifique est une aventure intellectuelle merveilleuse. C'est même une aventure tout court, parfois. Nous avons choisi cette année le thème du Soleil parce que c'est un thème qui, à la fois, est un thème d'astronomie, d'astrophysique. Comment le Soleil s'est-il formé? Qu'est-ce qui se passe dans son intérieur? Comment on peut utiliser son énergie? Quelle est l'influence de ces variations de luminosité sur le climat de la Terre? Ce sont un tout petit peu les 4 thèmes des conférences de cette année. Avant de vous dire quelques mots sur les 3 conférenciers d'aujourd'hui, j'aimerais juste vous faire mention qu'en plus de ces 4 conférences, il y a un spectacle son et lumière que vous aurez l'occasion de voir à la fin de cette journée. De fait, cette journée se passera comme suit. D'abord, il y a cette présentation qui se passe ici dans cet auditoire, et vous aurez la possibilité de communiquer, de poser des questions aux conférenciers qui sont là, et ils seront très heureux de vous répondre. Comme ils sont tous de langue maternelle anglaise, vous aurez possibilité d'écouter la version française en mettant les casques. Et puis de même, vous pourrez évidemment poser vos questions en français, elles seront traduites en anglais. Ensuite, après cette partie, je dirais, de discussion, de débat entre vous et nos conférenciers, il y aura un petit lunch qui sera servi à l'extérieur de cet auditoire. Et puis, par petits groupes, vous allez visiter l'observatoire avec des étudiants qui vous amèneront à travers les arcanes de cet institut. Après quoi, il y aura le retour à Genève vers les 2h30, 3h. Et puis là, nous allons rencontrer les personnes qui ont fait le spectacle, Son et Lumière, qui vous indiqueront, qui vous raconteront un tout petit peu les coulisses, comment ce spectacle a été fabriqué. Et ensuite, la journée se terminera par la vision de ce spectacle. Voilà. Alors, j'ai le plaisir aujourd'hui d'accueillir 3 éminents scientifiques. Tout à votre gauche, vous avez le professeur Art MacDonald. Je ne vais pas faire une longue description de chacun d'eux, je vais juste dire un mot. Art MacDonald a été le directeur du Sudbury Observatory. C'est un observatoire extraordinairement étrange. Étrange parce qu'il observe le Soleil depuis une région qui est sous la Terre, 2000 mètres sous la Terre. Et en fait, hier, Art a donné une magnifique conférence où il expliquait toute l'aventure que ça a été de construire ce détecteur. Et en fait, il vous donnera quelques indications tout à l'heure sur ce qu'ils ont découvert. Comment est-ce qu'on peut voir le centre du Soleil en se mettant sous terre? Ensuite, Jerry Mill, lui, il s'intéresse à la climatologie, à l'évolution à long terme du climat. Et c'est un des grands spécialistes mondiaux de l'impact de la variation d'irradiance du Soleil sur le climat de la Terre. Et il a en fait reçu un prix Nobel en 2007, qui est le prix Nobel de la paix, qui a été donné à, je ne me souviens plus exactement le nom de cette organisation internationale, mais qui produit ce que l'on appelle les rapports du GIEC. Il est d'ailleurs un des auteurs principaux de ce rapport du GIEC, en tout cas durant certaines années, qui justement avertit les pouvoirs politiques des mesures à prendre pour essayer d'éviter un réchauffement climatique trop important. Et enfin, le troisième conférencier est le professeur Daniel Nocera. J'ai oublié de dire que Art MacDonald vient de la Queen's University près de Ontario au Canada, Jerry Mill de l'Université de Colorado à Boulder, et Daniel Nocera est professeur à Harvard. Il vient juste de déménager du MIT à Harvard cette année, non, c'est l'année passée, en 2013. Le professeur Nocera est le pionnier de l'utilisation de l'énergie solaire à la manière des plantes, à la manière des feuilles des arbres. Et en fait, il a fait une invention qui a été citée comme une des inventions les plus importantes des dernières années, qui est une feuille artificielle, qui permet justement de capter l'énergie solaire et de l'utiliser comme le font à peu près les plantes dans les arbres. Ce sera le thème de la conférence de vendredi soir, et Jerry Mill donnera la conférence de jeudi soir. Voilà, je crois que j'ai plus ou moins tout dit. Chacun d'entre vous est invité maintenant à dire quelques mots, à vous présenter, à peut-être dire quelques mots aussi sur votre science. Ce serait entre 5 et 10 minutes chacun. Et après quoi, eh bien, la discussion sera ouverte entre vous et les conférenciers. Et je passe la parole à Art MacDonald.
Microphone, I better have it turned on. A great pleasure to be here and to be able to talk to you about what we do. What I do is kind of unusual, as was said. Normal astronomy and what you will see later today uses the photons of light that come from the stars or the sun, which is what you're seeing on the screen right now is a picture of the sun using photons. But it turns out that if you want to try to understand what's happening in the center of the sun, photons don't work, because actually what's happening in the center of the sun, if you make a change there, it takes about 100,000 years for the photons to make for the radiation to make its way out to the surface of the sun and make a change in the overall average temperature on the surface. And so there are particles known as neutrinos, which I'll tell you about in a moment, which are quite remarkable in that they are able to penetrate through enormous amounts of matter. They only stop if they hit the nucleus of an atom or one of the electrons going around the nucleus of an atom head on. And so they can go through billion kilometers of lead, the distance light travels in a year through lead, with only a 50% chance of hitting something, which means in terms of getting information from the core of the sun, they're ideal. On the other hand, they're damn hard to detect. They are very weakly interacting, and therefore we have to use a detector the size of a 10-story building in order to get a observed signal once an hour from these particles. However, we've been able to do that, and the reason that they are of interest is that it is now quite conclusively shown that the nuclear reactions that power the sun are the ones that you see on the screen behind me. The first one, 2p plus p, goes to 2h, which is deuterium. It's hydrogen with an extra neutron in the nucleus, is the reaction that is predominant in the sun. But there's a whole sequence of other reactions, and in the process of these nuclear reactions, you emit these quantities called neutrinos, and by observing these neutrinos, you're able to understand how many of these reactions are taking place as a function of time, and understand how the energy is being generated in the sun. And you see at the bottom an equation that shows the amount of energy that is given out as 4 protons are converted into a helium nucleus. It's a substantial amount of energy. It's millions of times greater for this nuclear reaction than you would have in any chemical burning of coal or anything like that. And that's why the sun has been able to survive for so long by powering itself with nuclear power. These neutrinos that are highlighted here come out over a range of energies. They are very substantial in their quantities. There's about 1 billion that goes through an area the size of your thumbnail every second from the sun, and maybe once in your lifetime a neutrino will hit one atom in your body and convert it into something else, and otherwise you're essentially oblivious to neutrinos. But they are, along with electrons and quarks, the fundamental building blocks of particle physics. They are the particles that we don't know how to subdivide any further. Neutrinos come in 3 types, electron, mu, and tau neutrinos. They are described by the standard model of elementary particles, the very same model that was verified to such a great degree by the discovery of the Higgs boson here in Geneva, announced in the last couple of years. They only stop, as I said, if they hit the nucleus of an atom or an electron head on, and yet they are produced substantially in the sun. Here they are in the classification of particles. Quarks and neutrinos and electrons, heavier electron types, mu's and tau's, form 3 generations of matter. On the right-hand side, there are the forces of matter. The gamma or photon is the electromagnetic force. The G for gluon is the strong force, and the Z and W are the forces for the weak interaction, which is much weaker than the other interactions, and that's all that neutrinos feel. They don't feel the strong or the electromagnetic interaction, and therefore they penetrate through matter extensively. Now, the standard model in its initial form had no mass for the neutrinos, had them not changing from one type to another as they are transported. That is something that we have been able to show is not true, and therefore we already know that there has to be an extension to the standard model, in particular the incorporation of neutrinos that do change from one form to another and have a finite mass. And that's the purpose of our experiment, was to do that, but also to test the models of the sun. Here you see what those solar models predict for the numbers of neutrinos as a function of their energy. And you'll see that there are substantially more pp neutrinos, as you see on the left of that diagram, than the other types. But when people started to measure these, starting back in the 1960s, what they found is that the measurements, represented by the blue lines here, were factors of 2 or 3 smaller than what is predicted by the theory, as represented by the multicolor lines showing the contributions from the various different emission properties in the sun. With the Sudbury Neutrino Observatory, or the SNO project, as we call it, if you ever visited Sudbury, Ontario, you'll understand why SNO is a pretty good name for the project, because the ground is covered by snow from December till March every year. We were able to use a material called heavy water, which gave us the opportunity not only to measure the type of neutrinos produced in the sun, the electron neutrinos, but also all neutrino types. And so whereas the other experiments were relying on the calculations for a comparison as to whether or not you were observing correct calculations in the sun, we were able to measure the other types of neutrinos as well. So if electron neutrinos were changing into another type, which is this theory I was saying was possible but not predicted in the standard model, then they would not have observed the neutrinos that had changed. We were able to also observe the ones that had changed. By comparing those two, we were able to show, in fact, that the neutrinos were changing, and that the problem which had arisen leading to these factors of 2 or 3 discrepancy was due to the physics of neutrinos and not due to the models of the sun. This is the detector itself. As I say, it's about the size of a 10-story building. It's 34 meters high. In the middle is about $300 million of this material called heavy water. About 1 in 7,000 of water molecules that you drink is actually heavier than other water molecules. Instead of H2O, it's D2O, deuterium oxide. Heavier due to a neutron. The neutron doesn't change the chemical properties of that type of hydrogen. If you go from hydrogen to deuterium, you change the weight, but not the chemical properties. So it behaves very much like ordinary water, but it has to be extracted chemically, and it becomes very expensive. It's used in a certain type of nuclear reactor, and we were able to borrow it for $1 for 10 years, which is not bad economically. Government was very good to us. We built this enormous detector. It took us about 5 years to do it. In the center of it is the heavy water in an enormous acrylic sphere, transparent, and therefore when there is a burst of light produced by a neutrino hitting the heavy water, we can see it with about 9,500 light sensors that cover the whole area and would be capable of observing a candle on the moon if you tried to use them in that way. By being 2 kilometers underground, we have shielded out the cosmic rays that otherwise would be essentially making our detector glow like the aurora borealis, which is the way in which the aurora borealis is created. It's by particles from outer space making the atmosphere glow. We have an effect from cosmic rays about a couple of times an hour, and they're very easily distinguishable. This whole thing is in a sealed cavity filled with ultra-pure water outside, and it is 2 kilometers underground. It's 6 Eiffel Towers down in a working mine. Everything that we had to put together to build the detector had to go down in the same cage that the miners and everything else travels in and be put together as a jigsaw puzzle when we're finished. This shows you the construction. We actually had Stephen Hawking visit twice, an amazing individual, and we had to be very careful in getting him there because normally everyone takes a shower after going through the mine. With him, we vacuumed him off in the first place and took him down in his wheelchair in a special container, a special rail car. Our water was a billion times cleaner than you are normally drinking, and that was necessary in order to make sure we weren't getting false signals from radioactivity. What we observed was that the number of neutrinos of all types matched exactly the solar model, whereas the electron neutrinos had been changing into these other types, which is of significance both for particle physics, because it points out that you have to extend the standard model, and is also of significance for understanding the sun. Because if you now compensate for these properties of neutrinos, you see that the measurements of ours, which are on the right of the screen, and measurements by other experiments match very well what is predicted by the solar models, leaving you with a great understanding of the sun and a strong support for a complete picture of how the elements in the universe have been created. Some of them are created in the Big Bang. The majority of them are created in stars or in supernova, which are collapses of stars after the star has burned out its nuclear energy. And as you can see, the yellow elements here are the ones that are produced in small stars like our sun. And so the sun actually is the origin, or stars like the sun, is the origin of carbon, nitrogen, and oxygen, which of course, along with hydrogen, are the elements of life. And so understanding that has been a major objective of our work. So I'll be happy to entertain any questions about this later on.
Thank you, Art. I will give the floor first to Jerry and after to Daniel for a few words of presentation.
Thanks, George. So I'm a climate scientist, which means I study the weather and the climate, and I try to understand how the climate system functions and how variability in climate interacts and is influenced by human activities, in addition to being influenced by natural phenomena like variability associated with the sun, with volcanic eruptions and other things. As I kind of look out at all of you, I'm kind of reminded of what I was thinking about when I was your age, and it may be instructive to give you a little insight as to how I ended up being a climate scientist. I actually, when I was your age, I thought I was going to be an architect. And the reason I thought I was going to be an architect was I really liked a lot of different subjects in school. I liked art, I liked science. In science, I liked biology and geology and dynamics and all these other subjects, and I liked photography, and I liked writing, and I liked all these other things. And so somehow I figured out that the combination of all those subjects would be architecture. I don't know what I was thinking, but I thought this would be a good idea. I was going to be an architect. So when I went to university, I started out as an architecture major, and I was studying architecture. Well, it wasn't going like I'd hoped at university, and I thought, you know, I'm really most interested in science. But what science? And this is maybe what some of you are facing. You may be interested in a lot of different kinds of science, and you may be trying to figure out, well, what kind of science would I maybe like to study? And so I was taking a lot of different courses of science, and I was trying to figure out what to major in, and I actually had taken an astronomy class. I had this great professor, and I thought, okay, this guy seems to really have an insight into all of this problem students are having. So I was going to go talk to him about what I should do with my life. And I'm standing outside his office waiting to go in, and he was talking to another student. As I was standing in the hallway, I was looking at the bulletin board outside of his office, and there was a poster on that bulletin board advertising a scientific meeting held somewhere in the United States, and it was talking about all these subjects related to weather and climate. I said, that's it. I've always been interested in weather and climate. So when I got in to talk to him, I said, how can I do something where I study weather and climate? He said, well, you can do it in this atmospheric science course. He said, but you're going to have to take more basic science classes. I said, okay, that's okay. He says, well, in climate science, since you're interested in all these different aspects of science, the climate system involves aspects of fluid dynamics, chemistry, biology, and all these other subjects that I was kind of interested in. So he said, but you're going to have to take more physics, more calculus, chemistry. And I said, okay, well, I can do that. So I ended up doing all that, and that's how I ended up being a climate scientist. So all these courses I took ended up being fairly relevant, as it turned out, because I ended up working with climate models, which are numerical models of the climate system that have equations from all these different areas of science. So there's the basic equations where if you've taken calculus already, they're nonlinear partial differential equations, so you can integrate them in time and get a time evolving state of the climate system. There's equations from physics involving land surface processes, ecosystems, which involve biology. There's atmospheric chemistry, so there's some equations involving chemistry. And so climate system models, which is what we kind of call them now, or Earth system models, are a collection of all these different parts of the climate system that involve a lot of different aspects of science. So it's turned out that all these things I ended up studying in school, and most of you won't be lucky in this regard, but I was lucky in that most of the subjects I studied actually were relevant to something I ended up doing for a job, that I actually get paid to do this kind of work, which is really interesting and really exciting, because it's also it's turned out to be very relevant because of the fact that humans are changing the climate system. And the big question is, how much of what we are doing, how much of this, burning fossil fuels, burning coal and oil and natural gas, how much of this is actually changing the climate? And so we know that there are natural phenomena that can influence the climate. Solar variability is one of them. The most kind of prominent part of solar variability is the 11-year sunspot cycle, where sunspots on the face of the sun actually come and go every 11 years. And they have a slight difference that makes a slight difference in the output of the solar radiation. But then there's also volcanic eruptions. If there's a big volcanic eruption, it cools off the climate because it shoots all kinds of dust and smoke, these particles we call aerosols, into the stratosphere. That reflects a little bit of sunlight for a couple of years, so that can cool off the climate for a while. So you've got these natural things going on, and you have also all these greenhouse gases that we're putting into the atmosphere by burning. We're burning, for energy sources, we're burning coal, oil, and natural gas, and so we know that's having an effect. So we try to understand physically what's happening in the climate system, and then we try to use climate models to understand how those natural processes are occurring or being affected by what we're doing. And of course, this is very important because if we're going to change what we're doing as a human society, if we're going to have to change our energy supply in some way, this has a big economic cost, and it's going to be a multi-generational problem. So this problem's not going away. So for our generation, we became aware of this, I think, for the first time and have documented a lot of it. We've got ideas of what could happen in the future. But for your generation, you're going to have to continue dealing with this problem in various ways. There will probably be technologies that will be invented that can deal with this, that can take carbon dioxide out of the air possibly and put it somewhere. Or we'll have alternative energy sources. Things Dan's going to talk about, I think, are very relevant. And so I think it's a very exciting time to be going into science, if that's what you're going to end up going into, because it's very relevant, it's really interesting, and it's exciting, and I think, at least from my experience, it's been a really worthwhile way to spend time. So, hand it over to Dan.
Thanks, Jerry. So I give the floor to Daniel now.
So I study energy, and I do more than calculations, even though I'm going to tell you about one calculation. And then I try to invent new things that will give you a better energy future than what you're doing now. So first we should say what you're doing now. You burn mostly oil, gas, and coal. And that all came from photosynthesis. And part of our climate change problem that you just heard about is because every year you're burning 1 million years worth of photosynthesis. So what took 1 million years to put in the ground to make oil, gas, and coal, to keep up with our energy needs, you're burning 1 million years of it. That's why you're putting so much CO2 into the atmosphere. And so we wanted to do a different type of energy source. And that's using the sun. There's good reasons to use the sun. Here's the best reason. I've never seen anybody get angry at the sun. They always smile at it. So that's a good sign. And then she follows you around. You feel when she's warm on you, and she's saying, use me, use me, use me. So I kept listening to the sun, so I decided I would abide by her and start using her. But let me tell you first a quick calculation. I'm going to do it for 35 years, so I want you to add 35 years to your age right now. And by that time, the world, you're going to need an extra 16 terawatt equivalents of energy. So what does that mean? So right now, the world is burning a 16 trillion watt light bulb. Now, watts is power, right? It's energy per unit time. So what you're doing is you're keeping a light bulb on that's 16 trillion watts. Not a 100 watt light bulb. It's a 16 trillion watt light bulb. And you need to keep that on. And you use mostly, like I said, coal, oil, and gas to keep the 16 trillion watt light bulb on. In 35 years from now, you're going to need another 16 trillion watts, or 16 terawatts of energy. And that sounds not so bad. 16, what's another 16? But we can do some calculations to tell you how hard that's going to be. So if you wanted to get half of the energy from, say, nuclear power, and by the way, I should get back, the sun is nuclear power. So I'm a huge fan of nuclear power at 93, way far away. So we'll let the sun do its nuclear chemistry, and then we'll just use its byproduct, the energy. But say I wanted to build nuclear power plants, and you need 16 terawatts. If I wanted 8 terawatts, when we build nuclear power plants, we try to build them at a gigawatt, because if they're much bigger, it's dangerous. And so if you take 8 terawatts and divide it by a gigawatt, you get 8,000. So that means if I want 8 terawatts of nuclear energy, I need to build 8,000 power plants, nuclear power plants. And that's in 40 years. Let's just round up. I said 35, but let's just go, say 40 years from now. So 8,000 divided by 40 is 200. So you need to build 200 nuclear power plants per year globally, or a nuclear power plant every 1.5 days to get half the energy you'll need in 35 years from now. And then you got to do that forever, because after you've built a nuclear power plant, after 50 years, you decommission it for safety. So after you spend 40 years building 8,000 nuclear power plants, they'll give you a 10-year rest, and then you got to start rebuilding them all again, because you have to decommission or take all the others offline. So that kind of gives you a feeling for how much energy you're going to need. If I wanted to use biomass, and I took all the biomass on the face of the planet, on the ground, and I had the fastest growing plants, you get 6 terawatts. Right? So no more eating, because I'm taking all your plants. So that's why a lot of us want to use the sun, because in 1 hour, the amount of energy from the sun that's hitting the face of the planet is what you use globally in an entire year. But we just don't do anything with it. And so what we decided to do is invent something that could take solar light. So what's the problem with the sun? When it's there, it's great. You can have a solar panel on your roof, but when the sun goes down, you don't have any energy. And so the real problem with any form of renewable energy, same with wind, is you can't store it. And that's what photosynthesis does, and that's what leaves do. Leaves take sunlight in, they use it in real time, just like you would a solar panel, but it also stores energy, and it makes carbohydrate. And so what we decided to do is try to invent out of dead things, because when things are living, you have to pay an energy price to keep them living. We used inorganic materials, so periodic table's gone, but the middle part of the periodic table, all right, we took that. You should always have a periodic table. There it is. So we used all the inorganic parts of the periodic table, especially the first row. You see the top one, manganese, iron, cobalt, nickel, copper, because those are the earth-abundant metals. And using those and then silicon, we were able to do what a leaf does, which is catch sunlight and then do the chemical reactions that store energy inside the leaf. And we've been able to do it at an efficiency that's 10 times greater than the leaf, because I don't have to use a lot of energy to keep my leaf alive, because it's already dead. So I really like dead stuff. Not dead humans, dead stuff. All right. So we invented this thing called the artificial leaf. Now, why do I think that's the way to go? So I'm going to, since George mentioned that this is about the sun, I'm going to tell you something today, and you're never going to forget it again. All right. Today, you're going to eat food, carbohydrate, and you think you're eating carbohydrate. But what you're really doing is chewing the sun. And I'm serious. So this is what happens. Sunlight comes into the leaf, and then what the leaf does, you give water to the plant. The leaf takes the water, and with the sunlight, it splits water to hydrogen and oxygen. So water is H2O. And so it rearranges the bonds of water and makes hydrogen and oxygen. It then breathes in CO2 from the atmosphere, and with the hydrogen, it makes carbohydrate. You then eat the carbohydrate, you breathe back out the CO2. When you break down the carbohydrate to get the CO2, you're left with hydrogen. You then breathe the oxygen in that the plant gave off when it made water. And then in your body, you have an enzyme called cytochrome C oxidase, which is the anti-leaf, and it takes the hydrogen and oxygen and recombines them to make water, and then it releases energy. So if you think about it, so scientists do what are called mass balances. Sunlight in plus water plus CO2 makes carbohydrate. You eat the carbohydrate, water back out, get the energy back out. So when you look at the full mass balance, and on Friday maybe I'll show that, you'll see that everything on this side that the plant's doing, you're undoing here, and the only new mass in the entire system is the photons from the sun. That's the only extra mass. So when you eat the carbohydrate, what's happened is sunlight has rearranged the bonds of water and CO2 to give you food, which you then eat and release the sun inside yourself, but in a more useful form called mitochondria. So when you eat any food, you should realize you're literally chewing a piece of the sun, all right? And that's worked for over 2.5 billion years. So I'm a real throwback in energy, and I've decided since it's worked for 2.5 billion years, I want to do that for the future, because remember, using coal, oil, and gas is only a new experiment on the world. We've only done that for 150 years, and we're messing it up quite a bit. That's what you're going to find out tomorrow night. And so this whole solar cycle is the way to go, in my opinion. It has enough energy. It's totally renewable. And then the question is how do you do it? And that's what that artificial leaf is all about.
Thank you, Daniel. Voilà, vous avez maintenant une petite indication sur ce chacun de nos conférenciers fait. Maintenant, la parole vous est donnée. J'espère que vous aurez des questions. Ne soyez pas trop timides, c'est très informel. Et donc, jetez-vous dans le... Soyez curieux. Donc, la parole est à vous. Qui veut se lancer ? Vous savez que, juste un petit mot, vous êtes tous plus brillants que le soleil. En fait, par unité de masse, un être vivant émet environ 1 watt par kilo. Le soleil émet un 10 millième de watt par kilo. Par unité de masse, en gros, vous êtes 10 000 fois plus brillant que le soleil. Allez, montrez votre brillance. Posez vos questions. Oui.
Pourriez-vous parler de votre parcours, comment vous êtes arrivé à étudier ce que vous étudiez actuellement?
I did these energy calculations when I was in my 20s, and it became obvious once you start doing these calculations, like I was mentioning, how much energy can you get from biomass, how much energy can you get from nuclear. It became obvious to me that sunlight should be the energy source. And why did I even start studying that? And none of you will know this, but in the late 70s there was an energy crisis, and we couldn't get oil in the western part of the world as easily as we do now. And so, as a matter of fact, in the late 1970s, the United States didn't even have a Department of Energy. after the oil crisis in the late 70s, the Atomic Energy Commission became the Department of Energy, United States Department of Energy. And so because of that crisis, I started studying energy. Then we got plenty of oil, and then everybody forgot about it again, but I didn't, because it was obvious from my calculations that we were going to be in big trouble someday. So that's why I started studying it.
Une autre question? You want to say? Okay.
When I went to university, for the first year, I knew that I liked mathematics and I knew that I liked science, but I didn't know what type of science I wanted to study. And many students that I've encountered in my career as a professor are in the same situation when they first go to university. But what I found, I tried a variety of science courses, and what I found was that physics was fun. And it was fun because the mathematics actually worked. In the things that you learn in the physics courses, you find that you can actually calculate how the world works and have it come out quite accurately. And so that was really the stimulus that got me to go into physics. I ended up doing graduate work at Caltech in Pasadena, in a laboratory where a lot of the nuclear reactions that I described to you today that are powering the sun were being studied in the laboratory. It was possible with a combination of experiment and theory to make measurements of things that when you applied the mathematics and the theory could explain very well what's happening in a bit of nature. And in fact, the leader of the laboratory I was working in at that time, William Fowler, got the Nobel Prize for understanding in detail how elements are produced in stars and supernova and so on. I spent my whole career actually doing various measurements where what one is trying to do is understand the fundamental physics underlying various processes in the universe. And the fun part of it is that you can do measurements that relate all the way from the most microscopic particles. We measured properties of neutrinos themselves. They're tiny. They're the smallest things we know, actually, in terms of particles, and we can understand them. And at the same time, we can use them to understand the sun, and they also play a role in how the universe has evolved since the Big Bang. So you can cover the whole field of the universe by getting involved in science and learning how to do something in detail. You see the three of us having fun and what we're doing. Everyone has a different inclination in terms of what turns you on for a particular field. But the good thing about it is the opportunities in university are there for you to find something that you really find fun and turn it into a career. And that's what's great about science.
Thanks.
You study climatology. So, what conclusions did you get to concerning the human involvement in the impact of the weather?
So how much are humans influencing climate is your question, right?
Yes.
Yeah, so that's, of course, that's the bottom line key question that everybody wants to know the answer to. So usually the answer starts out with, we know for sure the climate is warming, because some people are still questioning that. But climate definitely is warming. We know this from multiple lines of evidence, not only from weather stations, but from melting glaciers and from even some species of plants and animals are moving around to adapt to new temperature regimes. So we know the climate's warming, and then so you're left with how much are the humans causing it. And we can get at this a couple of different ways. Probably the most dramatic way we've been able to do it is using climate models, which are these sets of equations that we can simulate the whole climate system. And what we do is we're able to use the climate models as a tool to try to simulate what we've already observed in the 20th century climate. So we can run the climate model and say we started out around in the late 1800s, and we started running along, and we say, okay, every time a volcanic eruption takes place, we put that in the climate model, and then we get the effects of the volcanic eruptions, and we can put in the changes in solar variability, and then we can start putting in the human-produced parts of it, like the greenhouse gases and carbon dioxide and other greenhouse gases have been increased that we've measured and observed. And we can then use the climate model to run with all of those things happening at the same time, and to see if we can get if we can reproduce the observed climate system, the observed evolution of the climate that we've already seen. And that's just kind of like a sanity check to see if the model, if we can believe anything it says. And usually we can get a fairly good simulation of the climate we've already observed when we've got all those factors in it, both the human-produced and the natural. And then we can use the model to do something we can't do in the real world, and that's take it apart piece by piece. Okay, so let's just run 20th century climate and only put in the volcanic eruptions. So we don't increase greenhouse gases, we don't have any solar variability, we don't have anything else going on. We just put in the volcanic eruptions, and we see what the climate system response is just to that one factor. Okay, and then we kind of document that in terms of how the system responds. Then we go back and say, okay, let's just put in the carbon dioxide produced by humans, the increased carbon dioxide. So we run the model just with that single factor going along, and then we see how the model responds to that. Okay, well then we get that kind of response pattern. Let's go back and let's just put in the solar variability all by itself. We do that. So we do this a number of times with all these different things that affect the climate system, but just one at a time. So we can actually study the system response to each one. And then we kind of look to see which one of these is closest to what we've actually observed with everything going on. And it turns out that if we just have the natural parts of the forcing, the so-called forcing, in other words, the volcanic eruptions and the solar variability, we can get a little bit of the warming that occurred in the early part of the 20th century, but we can't get the warming that we saw in the latter part of the 20th century. So that experiment is basically the experiment, what if there were no humans on the planet? What if there were only volcanic eruptions and solar variability? And we see that temperatures went up a little bit and then kind of flattened out. But then we can add in the human-produced parts, the increasing greenhouse gases, and then that's when we see the big warming that we saw in the latter part of the century. And so we can see that in terms of the global average temperatures, that we can only get that warming when we put in the human-produced parts, and then we can actually look at the patterns of temperature, where it gets relatively warmer and where it gets maybe not quite as warm. And each of one of these has kind of a fingerprint of this pattern of temperature response. And then we look for those patterns in the observed records that we've got and see if we can match the fingerprints. Basically, you say, okay, warming from increasing CO2 has usually greater warming over the continents than over oceans, greater warming over the Arctic than over the Antarctic, and that's kind of a fingerprint of increasing CO2, and we can then see what the actual warming was in the system, and that's pretty much what we've observed in the 20th century. The Arctic's warm more than the Antarctic, continents have warmed more than oceans. And so that's another way of kind of trying to attribute cause and effect as to what part of these factors that affect the climate system are actually the most important. And that gets us to our conclusion that humans have caused most of the warming, at least since the middle of the 20th century.
Thank you. We have a lot of young ladies here today, I see, and I was wondering what you could share to encourage these young ladies that this is not just a guy's world, and that, you know, that there is a future for young women in science and in your fields and the people you work with.
Well, I have a group of 35 PhD students, and half of them are female. So, actually, you know, it's interesting. Scientists, there's this selection of female, male now. So all of women should become scientists so we can solve the problem. But scientists are kind of interesting people. We don't care I don't care what country he comes from. If he has a leg coming out of his head, we don't care about that, because what we deal with is science and this intrinsic thing. So while the world is fighting and there's different countries that are at war with each other, that's just not how scientists think. And we don't think like that in a gender-specific way. The problem is, at your age, there are a lot of negative feedback loops that keep, that might start differentiating. But I just want to assure you, when you get to the university level, and if you go into science, scientists are just blind to that, and we're blind to colors of people and what they look like and who they are, because we really just deal with science. That's how we view each other. That's also bad, because sometimes we're terrible in public, and nobody wants to dance with us and talk to us, but what can you do? But I will tell you, half my group is female, and there's no problem. And I also want to say one other thing. I like coming to Geneva in Switzerland because you guys are the best trained science and math students in the world. You probably know that, especially compared to America. So you guys are our hope, so we really need you to become scientists.
And I may add a little bit to that. When I was a student at university, all of my professors were male. I can't think of a single female professor I had in any science course I ever had. But my fellow students were probably about half were female. When I got to grad school, probably about a third of my fellow students in graduate school were female. But I could see that the undergrads coming up behind us, there were maybe 2/3 were female and 1/3 were male in the science classes. When I got to the National Center for Atmospheric Research, where I work now, when I was hired, I was really just out of school, and so there were hardly any female scientists at the time. And in fact, some of these older scientists that I was dealing with, they were kind of idiots anyway. I mean, they were kind of jerks, and they had these big egos, and we're thinking, what's with these guys? And so they seemed to be kind of standoffish to everybody, including young students like me. But there was several female young scientists that were hired right along about the same time I was hired. And then as we get succeedingly younger scientists coming in, there's more and more women that are coming up. So I think what's happening is we're seeing, just in the time I've been doing this, I've seen a real transition in the number of women that are doing science. And now when we get postdoc applications, it's usually 50-50 for postdocs that are coming out that want to do study beyond their graduate careers. And just one final example, I'm involved with a World Meteorological Organization unit called the World Climate Research Program, which kind of coordinates climate science internationally. And there's a lot of panels and working groups. And one of the panels, or the working groups I've been on for a long time is called the Working Group on Coupled Models. And this is basically a committee that has representatives from all the big climate modeling groups around the world. There's about 30 high-end climate modeling groups around the world right now. And right now, we just this last year, we made history because for the first time ever in the WCRP on one of these panels, both the co-chairs are women, Sandrine Boney from France and Kath Senior from the UK, and the head of what's called the Coupled Modeling and Comparison Project, which basically coordinates all of these climate model experiments that we do to look at future climate change, is Veronica Eyring. She's from Germany. So for the first time ever, all the three positions that are leadership positions on this panel, this international panel, are women. So I think it is really going through a transition, and I think that's really a great thing for science and for all of us, because as males, just in the time I've been going to scientific meetings, when it was all males, you get this kind of weird male dynamic that all these guys are just kind of talking about guy stuff. But now that there's more women, it's actually a much more civilized kind of environment. And the males are behaving better, and they're not being as big of jerks as they used to be.
Yeah, I would echo all of those comments, we have about 40% female component in our group, and physics often is physics and math are the areas where there have been historically the fewer numbers of females compared to other disciplines like biology, for example. But I think there's a real trend to change that. I serve on a number of review committees for departments and institutes and so on. There's a very strong consciousness of the importance of being gender neutral in terms of the way in which the science is being handled to behave in the way that Daniel was describing, of simply dealing with the quality of the individual, and particularly the enthusiasm that individual brings for the work they're doing. And so I see a trend even in physics and math towards increasing female participation, which, as was just said, is generally regarded by us males as a really good thing. So that's my perspective on where we're going.
I have maybe just 3 remarks about that. The first one is that CERN has just elected a new director general who will be a woman. The second point is that a few decades ago there was a woman professor very famous because she discovered lithium at the surface of the sun. It was Professor Edith Müller. And finally, the only person who got 2 times the Nobel Prize is Marie Curie. She was a woman. Okay, let us continue with the questions. Please.
Oui, j'ai une question pour Monsieur Nocera. Donc, si j'ai bien compris, il travaille sur la conversion de l'énergie lumineuse pour essayer de faire quelque chose qui ressemblerait donc à une feuille artificielle. Et j'aimerais savoir si le succès de ces opérations, est-ce qu'on arrive à stocker sous une forme de carbohydrate ou autre de l'énergie solaire aujourd'hui, et quels sont les espoirs dans ce domaine? Merci.
Yes. So when the sun is out, realize when the sun is shining, you can use your solar panels, and they can power your house. But the sun goes down, and a real energy supply needs to be on all the time or available all the time. And so my feeling is the real key to solar energy is storage, which is what you're bringing up. And as a matter of fact, I don't want to get into all the economics, but you want to put a solar panel on your roof. And it's expensive. People will say it's expensive. And it's not really that expensive. It's just that coal, oil, and gas are too cheap because they're way more expensive than you'd think, because they're changing the climate and they're causing water problems and there's health problems. But we don't value that. But the bottom line is, to put a solar panel on your roof, it's expensive. But if you had storage, and say a power company could store the energy that you're generating, then it's to their benefit for you to have a solar panel, because you could generate energy for them, they could store it, and then sell it back to you. And so energy becomes a commodity. So in this part of the world, where you have a grid and you have power stations, if the power companies have a way to store energy, it's to their benefit for them to have you use solar, because they can make money off of it. So that's what I call in the legacy world, the world where you have inherited energy. Then there's the part of the emerging world, and they don't have any power companies and they don't have grids. And then in that instance, I believe a better model is distributed, where your own home will be its own power station and gas station. So there you could generate your energy locally and actually just use it in real time. And again, you're going to need storage. And so you're exactly right. All the inventions we work on, we don't worry about generation right now because silicon is working really well, and China is producing a lot of silicon. But the real crux of, in my opinion, of renewable energy is this way to do storage, and that's what the artificial leaf does. Is because once you split the water and you have hydrogen and oxygen, you can store the hydrogen and then use it at night. And you might not like hydrogen. So if you don't like hydrogen, this will just be coming out. We haven't published this yet. We've engineered little bacteria that breathe the hydrogen in, and they breathe the carbon dioxide in, and they make liquid fuels. But again, it's a storage problem, so you're exactly right. I think that's the key to the whole problem in renewables.
Yes.
How come at night, when we look at the sky, we see darkness and not stars everywhere? Because if there's the galaxy and we're here, we should see only a sort of blanket of stars like shining. How come there's black spots everywhere?
Well, part of the reason is that our galaxy is made up of matter that's referred to as dark matter. In other words, it's material that does not glow. We think that it is, in fact, particles that were produced in the Big Bang, and they are typically so massive that we have never observed them directly in any of our experiments on Earth, even at the Large Hadron Collider here in Geneva, because there simply hasn't been enough energy to produce the mass of such a particle. And so there's a very complementary program going on between the work that's happening here at the Large Hadron Collider and the sorts of measurements that we are making in our underground laboratory on a completely separate approach. Here at the Large Hadron Collider, you will hear them talking about the possibility of observing dark matter, and what they're talking about is the fact that there are theories that go beyond the standard model for a greater unification of the forces of nature that predict that there are weakly interacting massive particles. We physicists love that because it spells out WIMPs. So here are WIMPs that we're looking for. So you've got a bunch of nerds looking for WIMPs as we go forward. These particles fit nicely into the theory, but they could easily be so massive they have not been observed so far at the Large Hadron Collider. They continue to increase their energy and intensity in order to do it. On the other hand, back in the Big Bang, there was sufficient energy to produce enough of these particles that, in fact, when you look at our galaxy, which is kind of, which is a spiral galaxy, it's kind of like a cinnamon roll, if you know what I mean, in terms of the pastry. The outer regions of it are moving so fast that if there were not about 5 times as much matter that is not glowing as you observe glowing, you wouldn't have the gravitational force to keep those fast-moving stars on the outer periphery of the galaxy from flying off into space. And so measurements of that form and other measurements that are made in detail by astronomers show us that there is a lot more matter of a different form than what we're made of. In the case of dark matter, it's thought to be about 5 times as much as ordinary matter. We know from the dynamics of the galaxy roughly how fast those particles are moving. We know roughly what their density is. And so we have experiments, other experiments than the one I was describing in our underground laboratory, where we are able to get rid of other forms of radioactivity. The one I'm working on uses about 4,000 kilograms of liquid argon as a medium to look for a small burst of light when one of these dark matter particles penetrates through the 2 kilometers of rock above us and produces a faint burst of light that we observe in our detector. We've been able to reduce the backgrounds in these detectors such that we would not get a burst of light from radioactivity more than about once a year. And at that sensitivity, we can push into the region of the predictions of these theories for what goes beyond the standard model with good sensitivity. And so our experiment actually will turn on in February of 2015, and we're very excited. This is one of the fantastic times in having worked for 5 years or so in building one of these big experiments, and suddenly you get the opportunity to be in front of a display screen looking for what's going to happen. So it's going to be a lot of fun in a few months' time. And what we're hoping to do is to find these dark matter particles left over from the Big Bang and holding our galaxy together.
Yes.
Be able to storage energy, or is it difficult to imagine something that could storage energy?
Yeah, so you're asking what type of storage. So it's interesting, most people don't realize this. All the solar energy is stored in water splitting to make hydrogen and oxygen. The plant then takes hydrogen and combines it with carbon dioxide at night in the dark. You don't store any more energy there. So then you have to store a bunch of hydrogen in compressed tanks. And that isn't easy to do, and we don't have an infrastructure for that. Even though I will tell you it's coming soon, because in certain parts of the world now we're making a lot of natural gas from what's called fracking. And this doesn't solve the problem because you still make CO2, but methane plus water in the one chemical step makes hydrogen. So I don't know if you guys noticed this, but a year ago, Toyota and Honda said they were going to become fuel cell company-based car companies, meaning you're going to have a hydrogen tank in the back of your car and you're going to drive it around, because they're banking on everybody having methane, and they've made what's called a little reformer to take the methane, make the hydrogen, and just pump the hydrogen right into your tank, and you'll just drive out. So your house will be its own gas station. This is coming. But you still have to have a lot of hydrogen everywhere. And so the way around that is to take hydrogen plus carbon dioxide and make liquid fuel, because you guys know how to do that. And that's a very doable thing, and there will be no problem with scale. Now, one thing you guys have to remember, I keep saying you're going to take water and split it to hydrogen and oxygen, and you might think, oh my gosh, we're going to run out of water. But that's not how it works, right? Because after you split the water to make hydrogen and oxygen, even if it's in a fuel, when you get the hydrogen back, the hydrogen plus O2 recombine, you get the energy out and you get water back again. So it's a closed cycle. And if I wanted to power the entire planet with water, this is another way to answer your question, which is the amount of storage I would need in water. It would be 5 times the amount of ammonia we use globally for fertilizer. So on a global scale, we're already using a huge amount of ammonia, and we can do that easily. And to power the entire planet to get this extra amount of energy we'll need in the future, I would only need 5 times that scale, which isn't very much, in basically a sort of artificial photosynthetic scheme. So you don't have any worries about that. You'll be fine.
Jérémy, Est-ce que vous pensez que le réchauffement climatique actuel est très inquiétant?
Yes, this is a very interesting question because sometimes people portray environmentalists, for example, as saying, we're headed for climate catastrophe. In other words, global warming is going to produce some kind of catastrophic impacts. And others say, well, it's no big deal. But at the root of that kind of question, science aside, are human values. So it's kind of a question of how much you value a system that has kind of sustained human beings for a very long time, and how much you care whether that system changes fairly significantly. So for example, we know that when you increase carbon dioxide in the air, you're forcing more CO2 into the surface layers of the ocean. That makes the ocean more acidic. And we know that a more acidic ocean has bad effects on coral reefs. We also know that when ocean temperatures get very warm, it has the effect of bleaching coral reefs. In other words, the coral reefs turn white. They do this because the algae that make the color in the coral reefs are living symbiotically with the little coral organisms that form the skeletons. And when the water temperatures get too warm, the coral kind of freaks out and it ejects the algae, and what's left is just the white coral skeletons, and they call that coral reef bleaching. And we know that when these bleaching events occur, a certain percent of the reefs don't come back, they die. And so we're already seeing that we're losing a certain number of coral reefs, both to increased ocean acidification and increased the bleaching events. So you say, okay, well, maybe if you live in Geneva, you don't care if 3/4 of the coral reefs die. Maybe that's not going to affect you directly. So maybe you can live with that, right? So this is a value judgment, right? So maybe if it doesn't affect you personally, it's no problem, right? You're not thinking about all the people who live in the tropics who eat fish that they catch on coral reefs, and the coral reefs have to be a healthy ecosystem to sustain the fish populations. Maybe you don't care about them. Maybe you figure, well, they can worry about their own food supply. I'll just worry about my food supply, and everybody's on their own. But everybody's connected at some level. So then the counter-argument to that is, if you start destabilizing food supplies in tropical countries because coral reefs are dying and they can't fish as much, that's going to be politically destabilizing. So it may end up affecting people who live in Geneva because there may be more human conflict and there may be more issues with kind of geopolitical kind of consequences. So there's all these unforeseen things that could happen, but in the end, it's still a human value judgment, is what you view as catastrophic and what you view as damaging, because everybody has their own sets of values. But I think what people are trying to get a better handle on, and this is where social science actually comes into the climate change problem. Social scientists are actually studying how humans value things and how people living in one part of the world view the welfare of people in other parts of the world. And in almost every climate change scenario that we look at in the future, there's winners and losers. Some people may be better off in a warmer climate. An example is always given of Canada, that possibly in central parts of Canada, which are now pretty cold and inhospitable, you'll actually be able to grow, say, more wheat or more food crops. So,
but what about the skiing?
And well, so that's another thing. So some people may be better off and some people may be worse off. So some parts of North America will get more dry. We see this happening already. So maybe that will affect them negatively. So in any kind of situation, you may have people that may benefit and people that may be damaged by it. So you kind of have to look at how people view human welfare of the planet and how much you care about what happens to people in other parts of the planet and how interconnected we think we all are. And I think we have this growing awareness now, especially in the last 10 or 20 years, that we really are all connected. And with the growth of electronic media, you can actually watch people in other parts of the world suffering. I mean, you can watch events happening in other parts of the world in real time and see these people are really suffering. And how's that going to affect our perception of how we identify with those people? Do we just not care about them? Do we not care that they're suffering because that's them suffering and not us? We're doing okay, so maybe that's good enough for us and they're on their own. Or do we care enough about the welfare of people elsewhere that we will take action, will affect our lifestyles, we affect what we do to maybe that will do some good for people somewhere else. So these are a lot of interesting kind of social science questions that really get to the fundamental aspects of our value systems and how we value our lifestyles in comparison to other people's lifestyles in other parts of the world. And that's where I think social science has now become a bigger part of the global change problem that has really emerged, because we have to understand how people view things. The other part, just one last thing about people, is social scientists are now studying questions like, how bad does it have to get before you make a decision to change what you're doing? And this kind of applies to your day-to-day life. So, if you're having a problem with a friend and maybe you can deal with some kind of conflict with a friend, but maybe if it gets really bad, then you may have to get another friend to help you kind of resolve a conflict or something. But at some point, you get to a trigger point where you decide you have to do something differently. And so in the climate change context, how bad does it have to get before you think you need to change what you're doing, change your lifestyle, change our energy system? And this is a social science question because it may be different for different people. And this is the same thing for if we're supplying climate change information to, say, a corporation. And we say, okay, we think there's going to be a 70% chance that by the year 2040, the precipitation in this region that you need to cool a power plant, you need rainfall and you need a lake to cool your power plant, there's a 70% chance your precipitation is going to decrease by 50%. Well, is 70% enough for them to make a decision? Is 70% certainty enough for them to make a decision to do something differently? Or does it need to be 80%? Or does it need to be 90% certain before they make a decision to do something? So these are all these kind of human things that are really an interesting part of this problem. So you can look at the physical science part of it, which is the parts that we look at. And then there's the social science and the human reaction to this. That's a whole nother dimension to this. And that's kind of a part of the problem that's getting more study now as we get into these areas where we think people will actually start making, and governments may start taking action to do something about this problem.
There may be room for some change in Canada. In Sudbury in February, on the surface, it's about minus 35 Celsius, whereas 2 kilometers underground, it's about 40 degrees plus Celsius. So it's a good motivation to go down and work in your laboratory on a nice cold winter day in Sudbury.
If you have examples of open questions, questions that you find interesting and that they are not answered today by our science, or maybe if this is, if you have an idea like this, or if not, the kind of questions that the PhD students in your groups try to answer, to give examples of things that are important and are not done or not known?
Well, in the field that I'm working in, there are very big global questions about understanding the universe as a whole. I mentioned that we think that the matter that we're made of, type of thing you find in the stars that glow and that are studied by the astronomy that we're going to see later in the observatory today, they make up about, at most, 5% of the total universe. About 25% of the universe is in fact thought to be these dark matter particles. We think they're particles of a certain type based on a whole variety of different astronomical measurements, many of them made by the advances of having satellite observatories. Then there's a whole 70% of the universe that is referred to as dark energy, which makes up an overall 100%, which we understand comes in these three components, but two of them we have no idea where they fit into the laws of physics as a whole. Dark energy is actually one way of describing the fact that when you learn in university that gravity is always an attractive force between two objects, it's not totally true. Einstein's equations of general relativity dealt with this by putting in the possibility of a repulsive force, but in point of fact, it had never been observed until 15 years ago. Einstein actually referred to it as my biggest mistake, so-called cosmological constant. But it turns out when people started studying supernova at very large distances, supernova where they could calibrate just how much light was being produced by a certain type of supernova, and then they used that information with respect to distance and measurements of the spectrum of the light coming from such supernova, which is something that's done in optical observatories. They found that if you looked at how fast they were moving away from us and how far away they were, it doesn't follow as though they were simply exploded away by the original Big Bang. In fact, there's a repulsive force that's making them accelerate to some degree. And that is described as this 70% of dark energy. So in physics and cosmology today, tremendous amounts of information has been obtained, particularly in the last 20 years by satellite measurements and to some degree by the types of underground or low radioactivity measurements I was talking about. But there's a tremendous amount to be answered and big questions. 95% of the universe to be identified in terms of its details. Some of it being attempted here at the Large Hadron Collider, some of it being attempted by astronomers, and some of it by people using particles to do astronomy. So lots of big questions.
Yeah, I'll just say for the students, you might not know actually what research is, because a lot of my students don't know it. And actually, I'm surprised sometimes when I talk to faculty, they don't know it, why they do research. So this is why we do research. It's because it's unknown it's just to teach ourselves. It's that simple. So you're learning from books now, but it turns out the things we study, and anybody who's at the very front of their field, the knowledge doesn't exist in a book because you're creating the new knowledge. And so once you understand that, there's always an infinite number of new questions and new things to be discovered. So I'll just give you just a little snippet. When a lot of people say, oh, we discovered the artificial leaf and we had to make these catalysts that split water. We didn't try doing that right out of the blocks. Over 25 years ago, it turns out when you split water, you have to take 4 electrons and there's 4 protons. And electrons are quantum mechanical, so they kind of spread out. And protons are more Newtonian, they're classical. And it turns out it's hard to couple quantum mechanics to classical things, and even in physics, but also in chemical reactions. And so when we started to study this problem, we realized people in chemistry and physical chemistry and physics had never timed an electron and proton. And so we set out with just using lasers to time an electron to a proton, because there was no book we could go into to find out how protons and electrons speak to each other in a chemical reaction. And then we invented this field called proton-coupled electron transfer, and that's taken a whole new form in what's called, in biology, because there's a whole bunch of enzymes that react by proton-coupled electron transfer. So a lot of my research group is known in biology for inventing proton-coupled electron transfer, but we didn't really care about biology. We were just trying to figure out how to split water. So that's just one example. But that's how we do research. It's because if it's not in a book, you do research to teach yourself so you can keep moving forward. So once you get into this, it's a little scary. I remember when I started graduate school, you're so used to reading and learning out of books, and then you're thrown in a lab and you just want to go find a book, and there's no book to read sometimes, right? You read books to get you to a stage, but then you have to kind of jump off the dock and just jump into the water and start discovering stuff. So that's a hard thing to do, but that's if you keep going on in your education, you'll learn how to do that. And so you should just know and we always say in science, if you do a good experiment, it will open 100 new questions. And that's the reason why.
Yeah, just to follow up on that a little bit, I remember when I first started grad school in my first year, and I was sitting there with my advisor, and we'd picked this problem. He'd picked it, actually, because I was just a first-year master's student. And he said, yeah, well, look at this, and go do this, and go do this. And he'd always have these great ideas, and I'm sitting there thinking, how's he coming up with this? So one day I asked him, I said, how do you know what to do next? You always seem to have a lot of ideas about what to do next, and I'll do these things, and then I'll be sitting there just puzzled about what's going on, and then you'd always have another idea about what to do. He said, I can't even tell you how that happens, but he says, it does happen eventually. And that wasn't a very good answer for me, because I thought, well, there's no formula to this apparently. I mean, you just somehow have to sense what to do next. But he was right, because at some point, like Daniel says, you get to the point where you look at one thing and you go, well, I wonder about what that is that goes next. And then one thing kind of leads to another. And it's almost like watching a crime scene investigation TV show, where a detective's trying to solve a mystery. And the detective's collecting evidence and trying to build up a case. And that's kind of how science works, because you're looking at something you don't understand. You say, well, how does this work? And you say, okay, well, let's look at this, and then if I look at that, then that raises this question, and then that leads you to the next thing. And so it does kind of lead you from one thing to the next, but there is no formula, and there's no real way to figure out what happens next, but it just kind of leads you along, because I think all scientists just are basically curious about how things work. And you start questioning, well, I wonder why that's doing that. And you look at something, and then you start asking questions, and then one thing leads to another. And just to give you an example, one of the great mysteries that everybody's really looking at right now is that for most of your lifetimes, actually, since about the year 2000, there hasn't been much global warming. And maybe you've heard people say on blogs and things that global warming has stopped, and they're right to a certain extent, because the temperature trend of global average temperature since about the year 2000 has been pretty flat. So that you look at this and you think, well, what's going on with that? So then you start collecting evidence. Say, well, okay, we can look at measurements of CO2 in the air. CO2 is still going up. CO2 is a greenhouse gas, so it should be trapping heat. Okay, is there any evidence for heat being trapped? You look at satellite measurements. Yep, the satellite measurements show that heat is still being trapped in the system. Okay, so where's the heat going? If it's not going to warm up the surface temperatures, okay, let's think. Land doesn't have much heat capacity. Ice and snow, no help there. It's got to be going into the ocean, right? This heat that's being trapped, if it's not warming up the surface, it's got to be going into the ocean. Let's look at measurements of the surface layers of the ocean. Nope, the surface layers of the ocean aren't warming up much. What's left? It's got to be the deep ocean, right? Okay, well, let's look at measurements there. Not many measurements of the deep ocean. So you don't have really good measurements of what the deep ocean temperatures are doing. We can look at climate models, and we can look at these periods in climate models that are internally generated periods where you don't get much warming. And sure enough, in the climate models, you see that the heat content of the deep ocean is going up in the climate models. So now let's go back and look at the limited observations we have from the real ocean. Sure enough, those are showing evidence of warming in the deep ocean. So global warming hasn't stopped, it's just happening in the deep ocean. Why is that happening? Well, let's look at the climate models again. Let's look at the observations again. The observations show that in the past 150 years, we have these decades, or even a 30-year period from the 40s to the 70s, when there wasn't much warming. In fact, the warming trend was almost flat, even though CO2 is increasing during that whole time. So what we're going through right now is not unprecedented. We can use climate models as a tool to give us some good clues as to what's happening. Then we go back and look at the limited observations we have to see if we get any insight from that. And then the last step, which is a kind of a new area of climate science, is let's see if we can predict these short-term fluctuations of climate. And this is a new area of climate science that's been around for only about 5 years. It's called decadal climate prediction. You take the climate models we use to run to the end of the 21st century, but we actually start them out with a specific observed state of the climate system, run them forward about 10 years and see if we can actually simulate the time evolution of this combination of naturally occurring variability, which produces these kind of flat periods of warming, which are these naturally occurring processes that mix heat into the deeper ocean, versus the response of the climate system to warming from CO2. So that's really at the frontier of what we're doing in climate science right now. But you can see how kind of one thing leads to another, and you keep asking questions, and you keep trying to figure out how the world works, and that kind of just drives it along.
Ok, nous arrivons au terme de cette rencontre. J'ai peut-être juste 2 petites informations pratiques et je dirais un petit mot de conclusion. Les 2 informations pratiques, c'est que tout à l'heure, vous aurez un repas, un lunch, et vous êtes invités à continuer la discussion avec chacun des conférenciers qui se feront un plaisir de discuter avec vous. La seconde, c'est qu'il y aura un bus vers les 2h30, 3h qui vous ramènera à Genève pour la partie plutôt spectacle. Et puis, quant à moi, j'aimerais dire 3 petits mots. La première, c'est qu'effectivement, la connaissance, c'est un tout petit peu comme la surface d'un cercle dont le rayon augmente avec le temps. Avec le temps, cette surface augmente, on connaît de plus en plus de choses. Mais la frontière du cercle, c'est la frontière avec l'inconnu. Et cette frontière aussi augmente avec le temps. Et comme l'a dit Daniel Nocera, quand on avance, de nouvelles questions apparaissent. Voilà, ça c'est mon premier point, cette analogie. Mon deuxième point, c'est que si vous voulez travailler à cette frontière, faire de la recherche, et que vous voulez étudier la physique, l'astrophysique et d'autres sciences, l'Université de Genève serait heureuse de vous accueillir. C'est une très bonne université, on y étudie les nouveaux mondes autour des exoplanètes, autour d'autres étoiles, on étudie les plus lointaines galaxies dans l'univers, on essaie de comprendre ce qui se passe quand on met des WIMPs dans le Soleil. Enfin, c'est vraiment une très bonne université. Et puis ma troisième pensée de ce jour, c'est de vous inviter à avoir l'ambition de vos rêves, de vos désirs, pas être ambitieux pour écraser les autres, mais être ambitieux pour donner le meilleur de vous-même. Et il y a cette très jolie phrase d'Oscar Wilde, il avait écrit visez la Lune, en cas d'échec, vous atterrirez dans les étoiles. Merci.